Okay, yeah, but Ivan, thank you very much, and I'm especially excited, to present it for Taiwanese Association because I spent like several years in E3, many years ago in Hsinchu, and I should say Wo-ai, Taiwan. It were those were my favorite years, in my life. I went everywhere, Kintin, Sun Moon Lake, Alisan, all of those places. Okay, so let me go to. Let me see where I can. Okay, so the outline, that indeed today, development of cost-effective and reliable photonic integration technology is like really the key to unlock the huge volume potential for photonics. Actually, if you look into all what's happening with AI right now, and I'll show a couple of slides on that there are billions of 200 gigabit per second equivalent optical channels will be needed, per year, and the number will keep growing. And the major key here, in order to really unlock this potential, is to make cost-effective and reliable photonic integration. Then I will briefly touch like technology landscape and competition. How do we see it at Alfalume? And say a few words about the company, and then we'll cover the topic why we believe quantum dot technology can really support such an effective integration because of those unique features which we have compared to traditional indium phosphide CWDB technology. This is picture, from actually father of modern data centers, Andy Bechtolsheim, co-founder of Arista, and it's a good point stated here that really like AI changed everything. So the demand, and it's not a bubble, it's not a telecom bubble like 20 years ago, it's real. And the demand of the power of those models is so big that actually what we do, this physical layer, we're not in time, to catch up. Even if we keep growing like crazy, like all those market prediction shows the potential growth, we still, cannot support that growth of what is envisioned for overall model's power. It's like, silicon is improving only 2 times for 2 years, and like photonics is still much worse till now. And it's interesting to see, that this is most reputed company in marketing, like counting in the United States, and these guys are changing their forecast every half a year, to higher to high number of channels, basically to high number of optical transceivers to be built. They keep growing every half a year. They keep growing their predictions, and now it's interesting to see where their own present the comparison of what they predicted in March and what they predict now in October 24. So also what we expect that the transition from 800 gig, let's say DRA transceiver, to 1.6 terabit will happen much faster than any predictions, even from such an optimistic agency as Light Counting. So we expect that really, and also when we calculate these numbers, we calculate not only bottom up, like Light Counting is doing, but also top down. When we look into the demand of those switch manufacturers, those guys who build those switches where you have to plug your transceivers. And we expect that really 1.6 terabit will start to dominate the market, by middle of 2026. And that's why all the technologies we're looking at, they have to support such a speed. Interesting slide from Malaga forum on photonics, which took place about 1 month ago. Now it's like picture getting famous because if you look into the left side, in integrated photonics, you have only 20% of value for your photonic chips, and 80% comes from packaging and testing. Whereas for electronics, for silicon, it's vice versa. So the main value is in the chip, and packaging and testing occupies much smaller percentage of that value. And now, recently NVIDIA even bypassed Apple in their market valuation. And this is unbelievable things, company which is making just silicon chips, they are now worth of much more than such a company as Apple. So if you look today into transceiver manufacturers, right, and majority of them are based in China, and the value inside of optical transceiver is distributed between three things. It's like DSP, photonics components, and assembly. Whereas once optical engine is developed, it means where you have a good coupling of lasers to silicon photonic modulators, then coupling of peak into fiber. And once LPOR is taken over, and you know, like there is a like pluggable using DSP, and then there is a very big push actually from Arista. They demonstrated that transceivers without DSP, but with much better design of PCB with good signal integrity, can be driven directly from ASIC, from good ASIC. And in this sense, the big value of overall transceiver world will come from laser, silicon photonics, and integration. And today, whatever people say, what we really see, only Intel has a true integration technology in the volume. You know, when they do wafer bonding of indium phosphide to silicon photonics. And there are tons of companies which are well-funded and which are developing, you know, this type of integration of laser to peak and fiber to peak. There are different technologies. I will skip it. You all know it, like edge coupling, vertical coupling, evanescent coupling. And there are pros and cons to be considered in different applications. There are, again, many activities to do flip chip on pedestal or to couple light butt coupling or microtransfer printing. Interesting technology of photonic wire bond from Vanguard. And also, let's say, if you talk about coupling of peak to fiber, there are a lot of developments of vertical coupling through grating and so on. All of them, you'll have slides, right? All of them have pros and cons. And obviously, if one can really mount laser on silicon photonic chip and do butt coupling, then potentially it might be the best approach. However, the challenge for standard quantum well devices is so-called reflection back. If you have reflection back on a level of -25, -30 dB, traditional indium phosphide DFB laser will suffer from losing its coherency. You know, your line, your DFB lines start to get noisy and wider. There are a lot of work going on around coupling fiber into peak, different activities, different companies. At least what really catches the eye today, what Intel developed using glass, you know, a coupler and a holder, and then connecting it with the fiber in passive alignment. And by the way, you know, I have been hearing, you know, like about like V grooves for years now. People talking about coupling fiber through V grooves, but at least what we know that till now, you know, final active alignment is still needed. So somehow this issue is not resolved either. If you look into different technologies which will compete in order to win this race for 200 gig per lambda, or actually now, like a few biggest companies, they decided to develop SerDes which can support 448 gigabit per second PAM4 or 228 gigabaud. They started to develop the silicon. And now there is another challenge for photonics. We even cannot do today in the volume 200 gig per lane, but people are pushing, you know, to go to 400 gig per lane. So there are different technologies competing. It's obviously silicon photonic and thin film lithium niobate, which is like external modulation. And in this case, you need CW DFB laser to support it, or array of those, or individual lasers. And then indium phosphide is EML. EML, by the way, now they claim they can do even 400 gig per lane. But the problem, you have 8 lasers for DR8 transceiver, and you have to couple individually each one of them. And the question also temperature stability, because when you push the speed, you know, always you push one parameter, you start to sacrifice on others. So it's not yet clear whether EML can compete with silicon photonic and maintain their shares. So we hope, as we build CW DFB laser, and hopefully there are good solutions for integrated photonics, that silicon photonic plus CW DFB laser will win this competition. And actually market forecasts are going in that a bigger and bigger share will be taken by silicon photonic or thin film lithium niobate plus CW lasers. Here, there is a prediction of, because SR8 is based on VCSEL, DR8 based on, let's say, silicon photonic and CW or EML. And even though it says like 500 meters, it's a standard, but majority of the link, especially to support AI clusters, it's like, below 100 meters. And another one is FR4 or FR8, when you have CWDM laser split it either by 20 nanometer or by 10 nanometer, if you talk about 10 of them. So that's why I hope, again, that silicon photonic will win against of VCSELs. So a few words about Inalume. Inalume is a company which is a spin-off from Yofa Institute, and our professor, Alfalume, he got Nobel Prize for semiconductor laser. Company was started in 2003, and really made some achievements in development of quantum dot technology. Actually, we were the first team who managed to bring quantum dots from research to commercial applications. And the reason, people very often ask me now when we present our results and they say, okay, you have been talking about quantum dots now for decades. Why the progress is so slow? And the reason for that is that quantum dots are very slow by themselves because of damping of relaxation oscillation, and you cannot modulate them fast. That's why quantum dot technology had to wait until external modulation technology is well developed. And now we expect that after some peak of innovations, excitement like 20 years ago, and now productivity phase is coming. So Inalume, it's a company in Germany. We run our own manufacturing facilities. Recently, we started to invest significant amount of money in order to bring CapEx to higher volume. And we will be also working with contract manufacturers and most likely in Taiwan in order to bring lasers to high volume manufacturing. There is a market, there are many of them where all-band lasers and SOA can support, and mainly, of course, it's cloud networking, AI clusters, and some others. Very interesting application of MCW LiDARs, where narrow line DFB is needed, which quantum dot can provide, and very high power boost optical amplifiers are also needed to substitute EDFA, which are used for 1.5 micron. And surprisingly, 1.3 micron turned out to be better eye safety and compared to 1.5 micron. So here's some record performance to demonstrate that indium arsenide, gallium arsenide quantum dots, DFB, can generate up to 125 degrees C, with a pretty good wall plug efficiency. Actually, nobody needs it, electronics doesn't work at this temperature, but 85, 105 degree, you can see pretty high power, unachievable in indium phosphide technology. So though, again, for pluggable transceivers, DR8, FR4, nobody needs power per channel more, let's say, than 150 milliwatt, and this is the product which we are ramping up right now. There was a nice demonstration at last OFC where two major transceiver companies showed performance, showed transceivers, LPO, it means linear drive without DSP, and quantum, instead of 4 DFB lasers for 8 channels, they used like 2 DFB quantum dot lasers for all 4 channels. And the main interesting things indeed, it's proven first time in the really production modes that we don't need optical isolator. Maybe it's not such a big deal, for active alignment for assembled transceivers, but once it comes to integration, it becomes very crucial parameter. So yeah, and I'll send you the link and very nice video recorded by Jose about this technology. So here's a measurement from our transceiver manufacturer partner, which demonstrates that quantum dot can sustain like minus 15 dB reflection back, and we expect it's about like 15 dB better compared to quantum well devices. There is interesting work going on also at Intel. They started, they do bonding of indium phosphide material to silicon photonic and build so-called hybrid lasers. But now they started to publish results claiming all those advantages of quantum dots. And there are recent publications on that if you bond gallium arsenide quantum dot wafer to your silicon platform, you might get certain advantage. Though, if I look into performance, so far it's worse compared to what they achieved with indium phosphide technology. So we also work, of course, on high-power DFB lasers for ALS, actually for co-package optics, because co-package optics is envisioned in two flavors. One is like having fully integrated lasers, another one having external light source, where you have, let's say, array of DFB, and then you intermix all lambdas into different fibers in order to bring one fiber with multiple lambda to support peak, which sits next to ASIC, and then to distribute the signal. The estimation one would need about like 6 to 8 such external light source for one AI chip in the future. And then you can easily calculate how many lasers are needed based on prediction how many AI chips will be built in the world in the future. So if talk about arrays, we also have to say something here compared to indium phosphide technology. But I should say, you know, the main advantage of this quantum dot technology, not just quantum dots, but gallium arsenide platform, because gallium arsenide is much more manufacturable compared to indium phosphide. If you think about silicon, you know, silicon is here in terms of manufacturability. Indium phosphide here, gallium arsenide not far from indium phosphide compared to silicon, but still, you know, you can do 6-inch wafers, you can, which is really much lower cost compared to indium phosphide technology. And the best solution, of course, to have co-package optics with single fiber bringing you several wavelengths instead of intermixing DFB array, because it gives you additional packaging challenges and losses in your AWG mixers. And this is the work we started to do many years ago. And now we feel it's like, you know, like a second win for comp laser, because quantum dots can also generate multiple wavelengths being coherent, precisely spaced, because these are Fabry-Perot modes. And then you have a single chip which can support multiple wavelength operation. Reliability. And this is a picture, you know, if I guess none of us remember, but if you think about it, you know, 70 years ago, those vacuum tube computers, they couldn't finish the simulation before some tuple failed. Now, if you look into AI clusters where people train the model, let's say, you know, keep going for 2 days, and they cannot afford failure of a single link. And estimation that laser failure is a root cause for about 80+% of hardware failures. Main failure today, by the way, link flap, and it's not yet clear what is the reason. But if you talk about hardware, then it's lasers. Quantum dots, you know, this is the picture from my PhD work in '99, before I went to Taiwan. In quantum dots, they have so-called like in situ window structure, because the typical reason for facet degradation that you have overheating on the facet and your band gap shrinks and then start to absorb photons which are coming from the bulk material. However, quantum dots emit light at longer wavelengths, and means shorter, bigger energy, smaller energy, and that's why they're not absorbed on the facet, of course, if you cleave your laser between quantum dots. And they're much less sensitive to dislocations, you know. So if you have quantum well, ideal quantum well, electron here, it's all the same. So all electrons will feel dislocations. But in quantum dots, of course, you have 3D localization, and that's why you are not that sensitive to it. Some reliability, some preliminary study from our customers, and pretty good results. We don't see basically any degradation. And these are our recent results. We're building now our machines for reliability. So here you can see even 105 degrees C. Statistics not big enough, but okay, we're building more. And these lasers, they have 135 degrees C PN junction temperature. We see some burning effect for 5%, and then it's stabilized. So far, we never observed like sudden failure of quantum dot laser. You know, if you do something wrong, they will degrade. But we never observed like in quantum well, you might have, you know, sudden failure. And that's why people do burn-in in order to select infant mortality of the laser. So far, we don't see it. And if you can prove it in the volume, then once you guys build your integrated solutions, because the challenge is, okay, you want to put many lasers into your silicon photonic chip, but how do you burn it? you will burn the whole optical engine. It might be too expensive, you know. But if your laser can have very, 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 very low infant mortality, then situation becomes much easier. So you bond them to silicon photonic, and then you burn in your overall peak with lasers without being scared that if one laser fail, the whole module will fail. And like few words about our recent really development, which is really interesting. So we developed semiconductor optical amplifier based on quantum dots, which can support several modulated lambdas traveling through it in one regime. It's similar to EDFA, like people use EDFA in telecom to amplify many modulated lines simultaneously, which is not the case for quantum wells because you will have too strong cross-gain modulation and lines will start talking to each other. On another side, if you run your quantum dot specially designed in high power, in high gain saturation mode, you can get very high power from a single stripe without tapered design with a very high efficiency, even at a high temperature. So that's why we say that with our quantum dots, we build kind of semiconductor analog of EDFA, which opens way to many other markets. And this is what I say about economics of gallium arsenide. You can use multiple wafer reactors. People sometimes are scared by MBE, but if you know how to run it, nothing to be scared, and there are big systems available. And to summarize, you know, we would say that quantum dot lasers can make life of silicon photonics easier because of high temperature operation, especially if you want to put your, you know, integrated engine inside of the box or close to your ASIC, then temperature is going to be high. We have to prove it in a volume, but we expect fundamentally better reliability. And obviously, gallium arsenide is better material for manufacturing. It's less fragile, it's cheaper. It's available on big wafers. Low alpha factor. This is a really cool advantage for integration, because otherwise, how do you integrate your laser and your silicon photonic? You don't want to put, you know, some ferromagnetic like optical isolator in between, and then single chip WDM capability, where either this is like single SOA with WDM function, or comp laser, or, you know, high yield DFB arrays. Thank you very much for your attention.